Imagine a world where robots can handle objects as gracefully as humans, making sure not a single item slips away. But here's where it gets controversial. Traditional robot design often relies on squeezing objects tighter to prevent slipping, which can damage delicate items. A team of researchers from the University of Lincoln, Toshiba Europe's Cambridge Research Laboratory, the University of Surrey, Arizona State University, and CAST has introduced a groundbreaking approach that mimics human-like movement adjustments instead of just tightening the grip. The inspiration for this innovative method came from a simple human experience, as explained by Amir Galamzan, the senior author of the study. When you're holding a slippery object and feel it starting to slip, you don't just squeeze harder. You subtly adjust your movements, slowing down, tilting, or repositioning your hand to keep hold of it, Galamzan said. Robots, on the other hand, have traditionally just relied on increasing grip force, which doesn't always work and can damage fragile objects. We wanted to see if we could train robots to behave more like humans in these scenarios. The researchers developed a controller that predicts when an object might slip from a robot's grasp and adjusts its movements accordingly. This controller uses a bio-inspired trajectory modulation strategy that complements conventional techniques for modulating grip force, enabling more dexterous manipulation. Essentially, it mimics how the human brain continuously predicts the outcomes of our actions and adjusts our movements to prevent slips. The team's approach allows robots to slow down, change direction, and adapt to the position and orientation of their hands in real time. Rather than just squeezing harder, this alternative strategy could significantly reduce the risk of breaking fragile objects during handling. It also works in situations where adjusting grip force isn't possible, enabling more fluid and intelligent interactions with a wide range of objects. The study presents two key breakthroughs. First, it introduces a motion-based slip controller that complements grip force-based control, especially valuable for handling fragile objects, wet or slippery surfaces, or hardware that doesn't support dynamic grip control. Second, it features a predictive controller powered by a learned tactile forward model, or world model, which allows robots to forecast slips based on their planned actions. The newly developed controller was tested in dynamic, unstructured environments and was found to significantly improve the stability of a robot's grasp in some cases, outperforming conventional controllers that rely solely on adjusting grip force. This is particularly exciting because embedding such a model into a predictive control loop has traditionally been too computationally demanding. Researchers are actively working to make their predictive controller faster and more efficient for real-time settings, exploring different architectural and algorithmic techniques to reduce computational overhead. They are also expanding their system to support more advanced and complex object manipulation tasks, including handling deformable objects or items that require two-handed manipulation. In the future, they plan to combine their approach with computer vision algorithms, allowing the controller to plan trajectories based on both tactile and visual information. Another important direction is improving the verifiability and explainability of these learned models. As we move toward more intelligent and autonomous systems, it's critical that humans can understand and trust how robots make decisions. For long-term vision is to develop predictive controllers that are not only effective, but also transparent and safe for real-world deployment. This research could contribute to the advancement of robotic systems, enabling them to safely handle various physical and potentially social interactions using a world model. This might allow robots to handle different objects in a wide range of real-world settings, including household environments, manufacturing sites, and healthcare facilities. What do you think? Could this approach revolutionize the way robots interact with objects? Share your thoughts in the comments below.